Today's talk is by John Taylor. John is a Cornish mining engineer who graduated from the Royal School of Mines, London in the mid-1960s. After graduation, he joined Rio Tinto and worked for them in Ireland, Iran and Rio Tinto in Spain. He then spent 20 years working for mining and exploration companies and consultancies around Australia from Kalgoorlie, Leicester to the west of Townsville in the northeast. During this time he worked and visited mining heritage sites in the USA, Canada, Philippines, Morocco and Zimbabwe. John has long been a mining heritage enthusiast, from exploring the tin and copper mines of Cornwall to the Roman mining sites of Spain, Cyprus and Iran, to many derelict outback mines of Australia. He moved to New Zealand in 1993 as project engineer on the Globe Progress gold mine in Reefton and has been based there ever since. He is New Zealand's reps on the Australian Institute of Mining and Metallurgy Heritage Committee and has been a long-term member of the Australasian Mining History Association. Over to you, John.
Now, this is the first time I've given a video presentation, so thanks to Edward for all his technology help with getting this going. I do a lot of video conferences, but normally I'm the listener, not the presenter. This talk today is one of 3 linked talks. This is the first one of the 3. And this talk today, as mentioned, Edward mentioned, is in 2 parts. First of all, it's a PowerPoint presentation introducing those who might not know that much about Cornish pumping technology. And it's followed by a video that shows actual Cornish beam engines, pump engines, actually working on operating mines in Cornwall in the late 1940s. So it's not those are not tourist videos, they're actual mines operating in reality in the 1940s. Now this first slide has a number of links to our part of the world. This head frame in the back and the big Cornish engine house behind it is the Taylor's shaft of the East Paul and Agar mine, Camborne, Cornwall, England. The links to this part of the world, the company that managed this mine was Bewick Mooring, or Buick Mooring, depending how you want to pronounce it, who obviously operated many of the mines in Western Australia in the early days. The other link to this part of the world is that the consulting engineer on this mine was a person called Dr. Malcolm McLaren, who graduated in New Zealand. Probably the greatest economic geologist that New Zealand ever produced. Apart from the fact most people in New Zealand have never heard of him. He moved overseas very early in his career and worked on every continent apart from Antarctica. When he died in 1936, Malcolm McLaren was described by the Times of London in his obituary as a million-mile geologist. In the days before aeroplanes, he travelled 1 million miles in his career and was a very, very renowned geologist. Produced the definitive book on gold deposits in 1906, and that's talk number 3. We'll do that sometime later in the year. Now, the other connection I have with this first slide is that in my final year of mining engineering at university, we had to do a major project, which normally was your supervisor would give you some fictitious data and you'd have to design a mine around it. That didn't really appeal to me, so I took on a project which was involved in reopening this mine shown in this slide. It's next door to South Crofty for anybody who's been to Cornwall, and 15 years after I did my project, the mine was reopened and was subsequently carried on mining. So that's a little bit of background of this first slide. Now, the Before Cornish Mining Technology was introduced, mines throughout the world were strictly restricted by the depth in which they could work by water. Everywhere in the world, mines ground to a halt when they got down into the water table, and a lot of those mines had massive inflows of water, and basically those mines ground to a halt. Now, when I worked in Spain, I was aware that the Romans had pumping technology. They were the reverse of a water wheel. They were treadmills powered by slaves. And at Rio Tinto in Spain, there were 4 of these big, huge 20-foot diameter treadmills underground that lifted water from one level to another level. Then another treadmill took it from that level up to a higher level. But obviously, that was fairly limited in how much water it could move. Back before this Cornish technology came on board, the only way you could dewater a mine really was by bailing it with a kibble, or there were sort of more modest schemes where you had this continual cableway on which rags were tied, and they would go down, soak up water, come back to surface, be squeezed out and go back down. But obviously the amount of water you could move by that was extremely limited. So just moving on with this presentation. Oh, Edward, it's not moving forward.
Just click on the screen and press page down.
Okay. Now, the story of Cornish technology starts with a person called Richard Trevithick, who was a Cornishman. He didn't actually develop the technology. Bolton and Watts probably built the first mine pumping scheme, but Richard Trevithick refined it extensively and into what the Cornish pump engines became. So Richard Trevithick is very well known. He was the first person to build a steam-driven railway engine, even though George Stephenson gets the credit for that. Richard Trevithick built a steam engine. Unfortunately, it ran around a circular track as a fairground amenity. Richard Trevithick also built the first steam-driven road vehicle, of which this is a picture of it. He built this as a bet that he could actually drive it from Camborne.
Well, Roger would be interested in this.
Yep. So this is
Roger,
this an actual working
the first steam engine.
Yep.
They claimed,
and
was built by this figure, Richard Trevithick, not
yep.
Stephenson.
Yep. So Richard Trevithick built this. Now, this is a replica of the original.
Well, look at this photo.
Sorry? So this is called the Puffing Devil. It actually operates. It's used on special occasions around Camborne to celebrate Richard Trevithick's unique inventions. Having trouble moving on with this. I don't know why.
Press the screen and page down again.
Yeah. Have I got to click on the screen every time?
I hope not.
Yeah. No, I didn't have to the other day. But
no.
Here's the Puffing Devil puffing around Camborne. Not a very good photograph. It's just blown up from a small. And these are the work squads doing its annual steam calibration and inspection. So Richard Trevithick really got stuck into building, stick railway engines and steam-driven traction vehicles, but he really got into becoming well known for the Cornish pumping engines. Now, you can see, obviously, this is part of your part of the world. One of the outstanding features of Cornish pumping technology is that they required these massive engine houses. You'll see later that the The beam that drove the pit work down the shaft weighed up to 60 tons and required massive buildings. So massive, in fact, that the reason most of these engine houses still exist around the world is they are so massive that they're a major effort in actually deconstructing and demolishing them. In a sense, even though they become representative of Cornish mining, you can appreciate that it's one of the failings of the Cornish technology that before you could install a pump on a mine, you had to build a massive engine house to house it. The second talk of this series, which will be next month, is the way after this Cornish technology was introduced, how people evolved from the Cornish into a more an easier scheme where you had a massive engine installed at ground level, but instead of having pistons that go up and down, as you'll see in a minute, the next bit of technology had a stationary engine, ground level, with a sideways piston, and translating that sideways motion of a piston into motion down the shaft. There's a scheme in New Zealand that actually had that technology, and that's going to be the next talk a month's time. Obviously, these engine houses exist around the world. Most of them are massive stone. This is one in New Zealand that's actually built in 1906 out of concrete, still there. It's such a renowned relic that this engine house was slid sideways because it's standing right on the edge of a pit, and the company needed to expand the pit. So the whole of this engine house was slid sideways on Teflon rollers. More Cornish engine houses. You can see how large and massive they are, and that's the reason they're still existing. Wallaroo. Obviously, you'll be seeing more of this when you go to Burra. So this technology went everywhere in the world. Engine houses, South Africa, Mexico, and yeah, wherever the Cornish miners went, they took their pumping technology with them. Those who don't know Cornwall, this was the innovative centre for mining in the sort of 1700s right through to 1880s. After that, Cornish mining started to suffer from other copper and tin mines coming on stream around the world that put Cornish mining out of business. And so at that stage, Cornish mining engineers and workers departed Cornwall and went to all the mining areas of the world, including Reefton, New Zealand. So here in Reefton, we actually have an old place called Cornish Town, where all the Cornish miners lived. I won't go into too much detail of this. I think this presentation is going to be made available to people, but lots of the terms of mining still used in the world came from Cornish mining. Winzes, rises. Now the Cornish were also quite interesting that all depths in Cornwall in mines were in fathoms, and the mine manager was called the mine captain. Not too sure, other than the fact that Cornwall is surrounded by sea, quite how the link went from the maritime use of fathoms and captains into mines. But that got taken out to other parts of the world. But I've been to places in Australia where all the old mine plans still had depths in fathoms. So I'm just having to click on the screen before. You can see the shaft depths here, all in fathoms. Obviously South Australia. and that mine went down to 420 fathoms. Hopefully most of you can remember that there's 6 feet to a fathom. So this basically is a simplified layout of a Cornish beam engine. This structure right up at the top is the balance beam. That weighed up to 60 tons. And on the left-hand side, you can see a single piston, which moved that beam up and down. And that vertical motion got transferred by the beam to downward motion on the rods going down the shaft on the right hand side. So the pump rods were called the pit work, and they went down the shaft and drove pumps at intervals down the shaft to pump the water to the surface. In the early days, the piston and cylinder on the left weren't actually driven by pressured steam. They were actually a vacuum engine called an atmospheric engine. Steam would be introduced into that cylinder, and once the steam was introduced, cold water was pumped into the cylinder, which condensed the steam and created a vacuum that pulled the piston down. So in the early versions of this engine, it was an atmospheric engine rather than a steam-driven piston. So this is a simplified diagram. This is quite a long presentation, so I won't go into too much detail. But if you want to really have a good look at this diagram afterwards, I think Edward's going to put it as a YouTube presentation. So the whole purpose of this is that the early engines were atmospheric engines, and the later engine then became high pressure steam engines. These are some of the details of a typical engine in Cornwall. 1832 built, 3 boilers, working at a pressure of 35 pounds per square inch, 6 strokes a minute. So these beam engines worked at a fairly slow, steady pace, but obviously rated 145 horsepower. And the stroke of the thing was, nearly 9 feet. And the timber work going down the shaft to drive the pumps, 14-inch square timber, and it's pumping 35 gallons each stroke from 265 fathoms. So if you multiply that by 6, it's obviously a lot of water coming up from deep down the shaft. Now, obviously, these engines required a lot of coal and a lot of water. The coal, obviously, there's no coal in Cornwall. All had to be imported from South Wales. This is a typical engine house. You can see the beam up in the top of the engine house. That's why the engine houses had to be so massive to support that 60-ton weight. And you can see the cylinder, whose piston was just going up and down in the cylinder, driving that beam in a up and down motion, transferring that to the pit work going down the shaft. Now, the idea of this engine is the beam at the top of the engine house wasn't designed to take the weight of all the rods going down the shaft. Now, you can appreciate 12-inch square timbers going 2,000 feet down the shaft would weigh a considerable amount. The weight of those timbers in the shaft were actually counterbalanced by using these balance bobs. So basically, this balance beam is linked to the rods and takes the weight of the rods by balancing it with scrap metal and rock in that balance box. So the idea is the beam in the engine house is actually just driving the pit work up and down, but the beam isn't supporting the weight of all these rods. That is independently counterbalanced by these balance boxes and balance bobs. This Cornish technology not only went down the shaft, it could be translated into horizontal motion, incline motion, and the Cornish were really innovative in being able to change the direction of motion from vertical motion to horizontal motion back to vertical motion. Sorry, I have to keep on pressing the screen here for some reason. Sorry, there's a bit of delay on. This is a typical mine in Cornwall, 1909. You can see the engine house with the steam engines inside, with the shaft behind it, housing the winding engine house plus the pumping engine house and the pump technology. This example of a balance beam, you can imagine this will, you'll now appreciate why these engine houses are so massive. You can imagine having one of those high up in the, an engine house. 90-inch bob, that's fairly standard. That would weigh 50 to 60 tons. This is a balance beam or balance bob in place. And that's just slowly going up and down, probably 9 strokes a minute or 10 strokes a minute, converting vertical motion from the piston into vertical motion of the rods down the shaft, which themselves are driving pumps in the shaft. Very simple technology. The video that is after this presentation shows how these people drove this technology. That's the cylinder head with the piston coming out of the top of it. These can be up to 100 inches wide. This is a 90-inch one. All the driving of these engines was mechanical, and the part of the video shows how the person actually started this engine in the first place. Once it started, everything was automatic from there on. This required intervention to start it. After that, all these gadgets did all the motion to keep the engine running without any human intervention at all. It's another one of the technology. The efficiency of an engine was a strange measure called duty, and there's a description there of what this duty is. Won't go into too much detail on that, but it sort of gives you the technical background of how these efficiency of these engines were measured. This is a construction of an engine house with the beam in place, and you can see the pit work going off down the shaft. Just a diagram of how they actually got this huge 50-60 ton beam up into place. Quite a novel way of sliding it into a pre-erected engine house and actually lifting it up and placing it in position. That's one of the cylinders, obviously 144-inch cylinder. Imagine building these in 1843. It's amazing what they accomplished in those days. And that's a milling wheel to mill one of these huge cylinders. So the Cornish engine, not only did it drive the shaft hauling and pumps, it also drove all the stampers. So you can see here where rods coming down from the engine house are turning a big wheel, which is connected right along that line of stamp batteries. So I mean, that looks like it must be 80 head stamper. Some more where the engine is converting vertical up and down motion into horizontal motion. And in some places it would actually be driving big pulley belts, driving all these tables. Now, this is a typical layout of a shaft, Cornish tin mine. Normally 2 or 3 compartments. One would be the hoisting compartment, and then another, well, quite often 2 compartments will be for hoisting and raising and lowering men. And another compartment with the ladderway and the pit work for the pumping, and the raising main, which is the big pipe on the left-hand side, up which the water is being forced by the down shaft pumps. Fairly motley crew of Cornish miners. Oh, sorry, these are South Australian miners. This just shows some of the pipe work involved in converting the down shaft motion of the pit work into pump motion. Now, there's a few slides coming up here which show this. So you can see on this right-hand diagram, the something looks like a fingerprint. That's the actual wooden rod going down the shaft, and actually that is driving a piston in a pump box, forcing the water from level to level. An example coming up now. Oh, in a minute. So the shaft pit work. Just give some examples. 50 or 70 foot long beams, all connected together. Wooden beams going down 290 fathoms, starting off 24 inches square at the surface, going down to 12 inches square right at the bottom of the sump. And amazingly, even for Cornish tin mines, a lot of that timber came from British Columbia. You can imagine sailing ships with these huge 70 foot long timber strapped to the deck. Now, this is an example. That center rod is the pit work. This is the incline shaft. If you look up the top right corner, you can see coming off that pit work, there is another beam bolted to the pit work, going down into that cylinder. And that subsidiary beam that's bolted to the pit work is actually driving a piston in this cylindrical pump, pumping water from this level up to the next level above, and then there'll be another similar pump higher up. So that beam, the pit work beam, is going up and down, and driving the pistons in the pumping water. Now you can see the massive raising mains involved. You can imagine having to move that underground with no mechanical power at all, just manpower and block and tackle, chains, everything. That's the bottom of the shaft. There's a this is sucking the water out as the shaft sinking with the air leg drill. This is a picture of the balance box that balance the weight of the beams down the shaft. So that's going up and down, and basically it's offsetting the weight of the rods down the shaft. Not only would you have one that is at the surface, you'd have a number of these balance bobs at various positions down the shaft, taking the weight of the rods. And as the shaft was deepened and more rods were added on at the bottom, they'd have to add extra weight into the boxes. This one's obviously full of granite blocks, but quite often use scrap metal and all sorts of things in there. Now, this is an example of one of the miners that had all these shafts. You can see that they're pumping 6.5 million gallons a day, equivalent to 27,000 tons of water each day. So you can appreciate Cornish Mining Technology really changed the mining world in being able to dewater very, very wet mines. Now, the Cornish are quite inventive in that on the left-hand diagram, at the top there, you can see the pit work, that vertical rod coming down the shaft. But by using a pivoting system, they could translate that vertical up and down motion into horizontal or into inclined motion on the bottom part of that slide. So the Cornish were really inventive being able to change the direction of motion from vertical to incline to horizontal. And there's all sorts of various schemes as to how to do that. I won't really spend much time on that one. Now, towards the end, the Cornish miners would quite often walk 5 to 10 miles to work in the morning. They would then climb 1,800 feet down ladderways to the bottom of the mine, work all day for 8 to 10 hour shift, then climb 1,800 feet up to the surface, and then walk for 5 to 10 miles home in the evening. That was obviously fairly inefficient in terms of manpower. So this inclined technology, the pitwork type technology, we had a beam slowly going up and down the shaft, was used to actually transport manpower. Now, the way this worked, in the bottom of that this picture, there's a platform with a miner standing on it. On the beam that's going up and down, probably 10 feet at a time, there's a little square platform attached to the beam that's going up and down. As the platform came down level with that bottom platform, the miner would step onto the small, now you can see the second miner from the bottom is standing on a small wooden platform attached to the beam. He is slowly being lifted up to that platform just above his head. He will then step off and wait for the beam to come down again, step on the next platform and would be lifted up to the platform above. Now, in the middle of the slide, there is another miner, fourth miner up. He's standing on the platform going up to the upper level. And this is called a man engine. The Cornish devised these things, quite efficient, until there was a massive mine disaster where the rods in the shaft broke, and all these miners on the man engine were killed as they got deposited down the shaft. So at that stage, the man engine technology started replaced by men riding in cages down the shaft. Obviously, after the Cornish beam engines with their type of technology, most pumping from underground was done by, and hoisting was done by steam engines. As I said, there was an intervening period where the Cornish technology got modified into a more efficient Cornish type scheme before these more modern engines came in back 1907. Typical Cornish tin mine, very narrow, tin loads, air leg mining. Even in days I worked down one of these one summer, they still had air legs. Nothing was mechanised in those days. You can see how, the width of the Stoke Geewar tin mine. I spent one summer working down here. As a mining student, I had to do 10 weeks underground before I could graduate. So I did part of my summer in the Cornish tin mine, next summer in the Norwegian iron ore mine, underground iron ore mine. Typical width of a tin load stoping. These are all the sort of specialised devices that the Cornish miners developed, and a lot of those are still used in mines nowadays. Cornish picks, special Cornish shovel, the Cornish miners could actually get some crushed ore on a shovel and swill it around in water and work out the tin grade of the ore they're mining. This is typical Cornish technology taken overseas to South Australia, and probably many of you have been to these sites anyway. So that's the first part of this talk. So it's over to you, Edward.